So these tests will be about the ratio root test, which is a test for absolute convergence. So we're going to go through both of these tests. And again, these are tests for absolute convergence. Now, to distinguish between the two, and we'll do both, the ratio test is often used when you have factorials or exponentials, whereas the root test that we're going to do is the one that you often use when you have nth powers. We'll show more of what that means. So let's start with the ratio. The ratio test, and it's a neat one. It's a nice one. Let the sum from n equals 1 to infinity of a sub n be a series with non-zero factors, or non-zero terms, I mean. And then we're going to check the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. This means checking the ratio of the nth term, or n plus 1th term, to the one that came right before it. If the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is less than 1, this series converges absolutely. If the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is greater than 1, it diverges. And finally, if the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n equals 1, it is inconclusive. So this is one of the harder parts, is knowing this kind of conditionality behind it, comparing it to the limit comparison test, which it's very similar to, and knowing that the limit comparison test just needs to approach a number, and having a sense of why that works should matter. So really what the ratio test is saying is what's happening to one term compared to one before it. This is sort of conclusively showing that the terms are decreasing enough to actually make kind of a difference between the two of them. This is showing that the terms themselves are increasing, and this is sort of like a, well, we're not really sure. So let's do an example. The sum from n equals 0 to infinity of 2 to the n over n factorial. So I said exponentials and factorials are where you use the ratio test. Let's check this. The limit as n approaches infinity. I'm going to back up here. Note how we really can't use any test other than the ratio test on this. I told you guys that we can kind of show that 2 times 2 times 2 times 2 over 1 times 2 times 3 times 4 times 5. The denominator blows up, and by nth term test this approaches 0. But I'm not sure about the sequence. The series. What's the series doing? I know the nth term approaches 0, but an nth term test is not a test for convergence. It's only a test for divergence. So we're going to do the limit as n approaches infinity of the absolute value of 2 to the n plus 1 over n plus 1 factorial, absolute value, divided by 2 to the n over n factorial. So that is plugging in the n plus 1th term and dividing it by the standard term. Well, that is the same as the limit as n approaches infinity of 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n. And if you simplify that, you're going to get the limit as n approaches infinity. 2 to the n plus 1 over 2 to the n is 2, divided by n plus 1 factorial under n factorial is just n plus 1, still an absolute value. And as n approaches infinity, this is equal to 0. Therefore, we can say the sum from n equals 1 to infinity of 2 to the n over n factorial converges absolutely by the ratio test. Okay, next example. The sum from n equals 0 to infinity of n squared times 2 to the n plus 1 over 3 to the n. Like a lot of our convergence tests, you have a clue about why this one may be the best test to use. The clue on this one is that it's composed of exponentials, multiple exponentials. You can't do you don't want to really worry about a direct comparison or a limit comparison with this, because you have this n squared in there that may throw things off. So we get the limit as n approaches infinity of, let's compare this, n plus 1 squared times 2 to the n plus 1 is 2 to the n plus 2 over 3 to the n plus 1, absolute value, times, I'm going to make the reciprocal, 3 to the n over n squared times 2 to the n plus 1, and we're going to simplify this. So when I simplify this, I want to simplify what I can, and let's not use any algebraic rules we don't know or can't use. 2 to the n plus 2 over 2 to the n plus 1 is 2. 3 to the n plus 1 divided by, or under 3 to the n is thirds, so I have 2 thirds. Let's keep the fraction bar going. Still have that n plus 1 squared and still have that n squared. And remember, we're doing limits, so I don't need to clean everything completely out, but as n approaches infinity, the ratio of the leading coefficients of these same degreed polynomials would be equal to 2/3. Or it would be equal to 1 to 1, so that's 2/3 from a limit, and that is definitely less than 1. Therefore, the sum from n equals 1 to infinity of n squared 2 to the n plus 1 over 3 to the n converges, and it converges absolutely by ratio test. Okay. Next one, sum from n equals 1 to infinity of n to the n over n factorial. So let's do the limit as n approaches infinity of n plus 1 raised to the n plus 1 over n plus 1 factorial times n factorial divided by n to the n. Well, I know that if I start to simplify this, and this is kind of the fun part of this, is making the simplifications happen. I have n plus 1 to the n plus 1. I know that these right here cancel to become just divided by n plus 1, because n plus 1 factorial under n factorial gives me n plus 1. And I still have that n to the n right here, so I could knock those out. Now I'm going to look at these. That is going to give me just n plus 1 to the n over n to the n, and which means that if I kind of pull that n out, I have the limit as n approaches infinity of n plus 1 over n raised to the n, which is the same as the limit as n approaches infinity of n. Well, let's divide that out to show you what this really is. This is 1 plus 1 over n to the nth power. Hey, that's familiar. You should know what that is. This whole thing is e. And if it's actually e to the first power. Remember, this k value here determines the power of the e. So since that's 1, this is 1. And e to the first is greater than 1. So the whole limit comparison becomes 1. Therefore, the sum from n equals n equals 1 to infinity of n to the n over n factorial diverges by ratio test. Final example of the ratio test, let's do the sum from n equals 1 to infinity of negative 1 to the nth power root n over n plus 1. So we're going to do the limit as n approaches infinity of the absolute value is going to knock out the negative 1 part. So I just get root n plus 1 over n plus 2 over root n times n over divided by n plus 1, which is the same as the limit as n approaches infinity of the square root of, see, when I divide these and do these by the reciprocal, which I probably should have done in this step, I'm going to do that here. We're just going to go times n plus 1 over root n. That's going to be easier to visualize. Then I get the limit as n approaches infinity of the absolute value of the big square root of n plus 1 over n times n plus 1 over n plus 2. This is ratio of leading coefficients everywhere. This right here, if I look at that radical, that gives me a, it may look like that's the same as what we did up above, but it's not to the nth power. That's not there. So this is not e. That's just the square root of 1. This is radical 1 times 1, which is 1. So therefore we have to say that this sum from n equals 1 to infinity of negative 1 to the n, root n over n plus 1, is inconclusive by ratio test. I would have to do something differently. What I could do differently is, let's kind of try this with a different thing. So let's check the alternating series convergence test. To do that, I'm going to reverse this and say, let's check that the limit as n approaches infinity of the root n over n plus 1, denominator degree is bigger than numerator degree, so that is 0. Then I'm going to check that the terms themselves decrease. I'm going to check that a sub n plus 1 is greater than a sub n. And I'm going to check that with let's do the derivative. We're going to let f of x equal root x over x plus 1. And I'm going to do f prime. So f prime of x is equal to low d high minus high d low over low low, which is, if I multiply by a 2 root x, let's multiply by 2 root x over 2 root x, I get x plus 1 minus 2x over x plus 1 squared times 2 root x, which is 1 minus x over 2 root x, x plus 1 squared. And that is less than 0 when x is greater than 1. Therefore, it's decreasing. So we've checked off both our boxes. So I can say now is that the sum from n equals 1 to infinity of negative 1 to the nth power, root n over n plus 1, converges conditionally by the alternating series convergence test. Okay. The next test is easier. We're only going to do one example of it, the root test. And what the root test says is that the sum from n equals 1 to infinity of a sub n converges absolutely when the limit as n approaches infinity of the nth root of the absolute value of a sub n is less than 1. I'm going to try to model this off of what we did up above, so I'm sorry if you've been taking these, and we'll say this means converges absolutely. Let's move that here. We're going to check the limit as n approaches infinity of the nth root of a sub n absolute value. Okay, that's better. I'll put a little bullet point there, bullet point here. The limit as n approaches infinity of the nth root of the absolute value of a sub n is greater than 1 means that it diverges. And like before, when the limit as n approaches infinity of the nth root of a sub n equals 1, it's inconclusive. So let's check this example. The sum from n equals 0 to infinity of e to the 2n over n to the n. And the key for this is that with the root test, it happens a lot when we have nth powers. So if you have nth powers, you want to use the nth root or the root test. So what I'm going to do is I'm going to check the limit as n approaches infinity of the nth root of e to the 2n over n to the n, which is the same as the limit as n approaches infinity of e to the 2n over n to the n raised to the 1 over nth power. When you do power of powers, you multiply, so I get the limit as n approaches infinity of e squared over n. And e squared is a constant, so this is equal to 0, which is less than 1. Therefore, the sum from n equals 0 to infinity of e to the 2n over n to the n converges absolutely by the root test. And we'll stop there.